Hi everyone. In this video, I'm going to start off by reviewing the frequency shifting and modulation properties of Fourier transform. The frequency shifting property states that if x of t has Fourier transform x of j omega, then for any real valued omega naught, x of t times e to the power j omega naught t has a Fourier transform x of j omega minus omega naught. And we see this because the Fourier transform of x of t e to j omega naught t is the integral from minus infinity to plus infinity of x of t e to the power j omega naught t, this whole thing times e to the minus j omega t dt, which equals the integral from minus infinity to infinity of x of t times e to the power minus j times omega minus omega naught t dt, and this is simply x of j omega minus omega naught. Note that we could have also derived this by using the frequency domain convolution property. So the Fourier transform of x of t e to the power j omega naught t equals the Fourier transform of x of t, which is x of j omega, convoluted with the Fourier transform of e to j omega naught t, which is delta of omega minus omega naught. And this here, the convolution of x of j omega with delta of omega minus omega naught, is simply x of j times omega minus omega naught. So the effect in the frequency domain of multiplying a signal x of t by a complex exponential is taking the spectrum of the input, x of j omega, and simply shifting it in frequency by an amount equal to the complex exponential frequency omega naught. Now, using the fact that cosine of omega naught t equals 1/2 e to the j omega naught t plus 1/2 e to the minus j omega naught t, we see that the Fourier transform of x of t times cosine of omega naught t equals 1/2 times x of j omega minus omega naught plus x of j times omega plus omega naught. And this is known as the modulation property of Fourier transform. So the effect in the frequency domain of multiplying by a cosine of omega naught t, is shifting the spectrum of the input x of j omega forwards by omega naught and backwards by minus omega naught, as well as scaling by a factor of 1/2. Now let's look at an amplitude modulation scheme called SuppressedCarrier amplitude modulation, or also called double sideband modulation. Suppose x of t is an audio signal that we want to transmit between two locations, and assume that this audio signal is band limited to omega b hertz. In double sideband modulation, our modulated carrier signal y of t is given by y of t equals x of t times cosine of omega ct, where omega c is the carrier frequency. So the Fourier transform y of j omega equals 1/2 times x of j omega minus omega naught plus x of j times omega plus omega naught. And this is due to the modulation property of the Fourier transform. This modulated carrier signal y of t is the signal that will get outputted from the transmitter and then picked up by the receiver. If we look graphically at the spectra of x of j omega and y of j omega, here's x of j omega versus omega, and then here's the Fourier transform of the modulated carrier signal y of j omega versus omega. And so as you can see, the spectrum of x of j omega has been shifted to the right to frequency omega c, and shifted to the left to a frequency of minus omega c, as well as being scaled down by 1/2. Now let's look at how we can construct a demodulator that recovers the original audio signal from our modulated carrier signal y of t. After transmitting the modulated carrier signal y of t to the intended destination, this double sideband modulated signal has to be demodulated to recover the original signal x of t. We can't use an envelope detector, since the envelope detector would return absolute value of x of t, not x of t, but it turns out that we can demodulate y of t using the following two steps. Step 1 is multiply y of t by an identical replica of the carrier signal. So z of t equals y of t times cosine of omega ct. And then step 2 is low pass filter the signal z of t with cutoff frequency omega b is less than omega cutoff is less than 2 omega c minus omega b. So in other words, the cutoff frequency of our low pass filter can be anywhere between omega b, the maximum frequency stored in our audio signal, and then twice the carrier frequency minus omega b. The reason this works is that the Fourier transform of z of t, which equals z of j omega, equals the Fourier transform of y of t cosine of omega ct, which equals 1/2 times y of j times omega minus omega c, plus 1/2 times y of j times omega plus omega c. And y of j omega is 1/2 x of j omega minus omega c plus 1/2 x of j omega plus omega c, which means that this expression evaluates to 1/4 x of j omega minus 2 omega c plus 1/4 x of j omega plus another 1/4 x of j omega plus 1/4 x of j omega plus 2 omega c. And this evaluates to 1/2 x of j omega plus 1/4 times x of j omega minus 2 omega c plus x of j times omega plus 2 omega c. The first term here, 1/2 x of j omega, is centered at dc f equals 0, and then the two components in the second term are centered at plus or minus 2 omega c. So by passing z of t through a low-pass filter, we can remove the spectra centered at plus or minus 2 omega c without affecting the original signal x of t. And by doing this, except for a scaling factor of 1/2, the final output of our double sideband demodulator would be the original signal x of t. Now usually the transmitter and the receiver are located at large distances from each other, which means that the receiver doesn't have an exact replica of the carrier signal cosine of omega ct to use here in the demodulator. However, this double sideband demodulation technique requires that the carrier frequency of the receiver demodulator is identical with that of the transmitter's modulator, and the two sinusoids are phase coherent, which means that they both have the same phase. And this is why the type of double sideband demodulator that we've just looked at is known as a synchronous or a coherent demodulator. It turns out that if the modulation carrier cosine of omega ct and then the demodulation carrier are not in sync with one another, so if there's a frequency offset or a phase offset, then there's significant distortion to the audio output, and in some cases, for instance, if there's a 90 degrees phase offset, then the audio signal could even disappear completely, so you wouldn't hear any audio. And this is why it can be useful to have an asynchronous or non-coherent demodulation scheme, which is what we'll look at in the next video.